All right, we're being recorded. Now we'll do the little trick. Looks like the little trick is not working. Okay, got it to work. Yay. Okay, folks, time to start. Today, the plan is to discuss spin orbit coupling, as well as a new trick for a new perturbation trick, which allows us to, which helps us to find the good basis, which we'll discuss more very shortly. Okay, so let's get going with spin. Let's start with by continuing our discussion of spin orbit coupling. And this is an important topic. It's very important in condensed matter physics, atomic physics, and chemistry, and maybe other places too. Okay, so the idea is that we have, let's do it for an atom. The hydrogen atom is the simplest one. We have the proton, we have the electron, which is zipping across, and the proton is creating an electric field, E, and because the electron is moving in the electric field, then in rest frame of the electron, then it feels a B field. And I wrote down the formula for that last time. I won't write it again. And so then that means that there's an energy, there's a new energy, which is negative mu of the electron, the magnetic moment dot that B. And that's just the Zeeman energy. Okay, so that's sort of the origin of spin orbit coupling. Okay, that's the energy. And we went through some math last time, some derivations, and we saw that we can write this Hamiltonian, the spin orbit, spin orbit Hamiltonian as some function of r, the distance of the electron from the center, from the nucleus, times L dot s, where L is the orbital angular momentum, and S is the spin angular momentum. And f of r, this function of r, is e squared over 8 pi epsilon naught times 1 over m squared c squared r cubed. Okay, and so that's spin orbit coupling. And so the question that we will now ask is, how does it change the energy levels? How does it change the energy levels of the electron in a hydrogen atom? In other words, we're going to have E, and the new energy levels are going to equal the old energy levels plus some change. I'll call that delta En, and that changes due to the spin-orbit coupling. And so, of course, the way that we find this out is going to be using perturbation theory, PERT theory. And we want to just go to first order and say that delta En is equal to, of course, psi n naught, spin orbit H prime, psi n naught. Okay, so that's sort of the strategy for how we're going to do it. And it's the same strategy we did for the relativistic correction that we talked about. But now we have to start asking ourselves those questions, those perturbation questions. So before we can plug into this very simple formula, because this is a simple formula that we love, but before we can use this very simple formula, we have to ask some questions. And the first question is, of course, are the levels degenerate? In other words, if I have the nth level, psi n naught, which has an energy En naught, is it degenerate? And remember, we're talking about the hydrogen atom. And so is it degenerate? Somebody tell me.
Yes.
Yeah, good. It's massively degenerate. What's the degeneracy? Can someone tell me like how many degenerate states there are for the nth state?
N squared.
Exactly. The degeneracy is equal to n squared. So I like to call that massive degeneracy. So there's degeneracy in a big way. And that's because of all the L's and M sub L's and M sub S's. That's where all the degeneracy comes from, the different angular momentum states, the different spin states. That creates huge degeneracy. Okay, so then we have to ask ourselves the second question is, which is, what? Can someone tell me the second question?
Is our like existing basis a good basis where like H prime is diagonal in the degenerate subspace?
Exactly, good. We have to ask, is it a good basis? That's right. In other words, are the off diagonal matrix elements, I should have just written it out, of H prime equal to 0. In other words, this is shorthand, this is the easier way to write it. Are these off diagonal matrix elements where M does not equal N in the degenerate subspace equal to 0? And another way of saying it is H prime diagonalized in the degenerate subspace? Is it diagonal in the degenerate subspace? These are all just different ways of saying the same thing. But I'm saying it many, many different ways, hoping that one of them will resonate with you and you'll pick whichever one you like the best. Okay, so we have to answer that question. And so that's not a completely trivial question to answer. And so there's different ways to answer that question. And today we'll discuss an elegant way of answering the question. But before doing the elegant way, I like to do it both ways. I like to see the brute force way and then the elegant way, so you can kind of understand. So it helps you to appreciate the elegant way. So we'll do an elegant treatment of this, but first let's do the not so elegant treatment, the brute force treatment. So let's answer this question using the brute force treatment. And using the brute force treatment, basically what we're going to do is we just calculate the off-diagonal matrix element. Calculate, this M H prime N, and just calculate and see if it's 0 or not. Just do it, brute force. So let's do it. So the basis gotta look at our basis state. So for the basis state that we're using is this one, our old friend psi n, n l m sub l, but there's one other quantum number. What's the other quantum number?
M sub S.
Yeah, exactly, because we also know that there's m sub s, because this is the one that tells me whether I'm, spin up or spin down, right? I'm going to erase that. That's right. So this is a way of writing the basis. Also, I should add that what I should really do also, there's a quantum number s, which is the total spin angular momentum. But for an electron, s is always 1/2. It never changes. It's built into the particle. So we just kind of ignore that one because that one's just kind of in the background. You know what I'm saying? But this one is really important because the particle could be up or down. So that's a really important one. So, okay, so that's our basis. And so then what we got to do is we got to calculate this matrix element. And so we'll do it like this. We'll say we got to calculate in the degenerate subspace, I have n, l, m sub l, m sub s. That's the one state. And I got to see if h prime connects it to another state, psi n, l, m sub l, m sub s. So now we got to calculate. We got to calculate this. But before that, we got to take a look at these subscripts. So this subscript, are these guys the same? This n and this n, are they the same? Yes or no?
Yes.
Are they? Yeah, good, because that defines the degenerate subspace. So yeah, definitely they are the same. But how about these guys? Can they be different? The L's, could they be different? Yes or no? Yeah, in the degenerate subspace, they could be different. So I'll just try that prime. And how about the M sub L's? Can they be different? Yeah, in the degenerate subspace, definitely. And the M sub S also. So this is the matrix element I have to calculate. The N's are the same, but the L, ML, and MS could all be different. And so I got to see what this thing equals. So let's calculate that thing. And so let's write that state in a way. I like to do this sort of in a bra and ket fashion. So let's do it like this. So this state here on the left, I can rewrite it as this. There's a radial component, which has quantum numbers n and l. There's there's the angular component, which has quantum numbers l, m sub l, the angular momentum part. And then, of course, there's the spin part, which is s, m sub s, right? And then here's my h prime, f of r, l dot s. And then on the other side, I'm going to have s is always the same. That never changes, but the m sub s could change. And the L could change. That's why I bring a prime on it. And the M sub L could change. That's why it gets a prime. And the R has the same N, but it could have a different L. Okay, so that's sort of the generic matrix element in the degenerate subspace. And so just to remind you, remember this is representing my Laguerre polynomial. This is representing my spherical harmonic. Right? Just so you remember, I don't want this to look too weird to you. And this is just representing my up and down states of spin. Okay, so let's calculate this thing. And so first, what we can do is I'll ask you, I have this, let's look at the radial part. I have this L dot S term. So is this L dot S term going to be acting on the radial part of the wave function? Yes or no?
No.
That's right, because angular momentum is always operating on the angular part. L acts on the angular part, and S, of course, acts on the spin part. And so this guy can slide right through but can he slide through this guy? Yes or no?
No.
That's right, because that has the radial variable in it. So he can't go past that guy. So I can rewrite this like this. I can take my radial parts, R and L, F of R, and I can separate it out, R and L prime. Okay, and so then I'm going to have my LM sub L and my M sub S states acting on the L dot S. So now I have the L dot S inside. But I'm going to write L dot S now. Now what I'm going to do, I'm going to write L dot S. I'm going to break it. I'm going to expand it. So L dot S I'm going to write as LX SX plus LY SY plus LZ SZ. And this is all acting on S MS prime, L prime, M sub L prime. Okay, so that's my matrix element. And so the question is this thing equal to 0, yes or no? And so let's take a look at it. Now, this part, when it hits these guys, these guys are eigenstates of this, and so they're going to come through. So this part, is this part going to end up being 0 or not? Because this guy, this is going to turn into a constant, which will get sandwiched by S, M sub S prime, L prime, M sub L prime, and S, MS, and L, oops, L, ML. So what is this thing equal to that I just drew? This.
It goes to 0 because the eigenstates are orthogonal.
Exactly, because I've chosen so that these guys are different. That's right, and they're orthogonal. So this thing clearly goes to 0. Good, because these quantum numbers are different, and so it goes to 0. Okay, so this guy I can ignore. But these guys, it's not so obvious, because when these guys act on this, these are not eigenstates anymore. And so what does it do? Well, it gets a little tricky, because you know that what's going to happen is that you're going to have Lx is equal to 1/2 L plus L minus, and Ly is going to be equal to 1/2I S plus minus S, oops, getting a little screwed up there. L plus minus L minus, and same for spin. We're going to get raising and lowering operators. And so those guys are going to start raising and lowering these guys. Oops. And so what's going to happen then is so what's going to happen is, let's just consider it. Let's consider just an example like the n equals 3 state. N equals 3 state. The n equals 3 state is going to have it's going to have L equals 0, L equals 1, and L equals 2 living inside of it. Now L equals 0 has how many states are in the L equals 0 manifold? How many? Somebody tell me. Shout it out.
1.
That's right, because M sub L is only 0. How about L equals 1? How many states are there?
3.
Yeah, exactly. 1, 2, 3. How about L equals 2? How many?
5.
That's right. 1, 2, 3, 4, 5. Okay, so these are the different manifolds. That's like a word that you can use to describe this little collection of states. And so you'll notice that you'll notice that when I look at this matrix element up here, this thing we're playing with, if I look at this matrix element, for the matrix element, if L does not equal L prime, then can you tell me what this matrix element is equal to? Because these guys, Lx and Sx and Ly and Sy are going to be raising these values, raising and lowering the values of M sub L prime and M sub S prime. That's what they do. They raise and lower those values. So if L does not equal to L prime for this thing, what does the matrix element equal? Somebody tell me.
0.
Yeah, that's right. Can you say why?
Well, it won't change that quantum number, so you'll still have orthogonal states.
That's exactly right. That's exactly right. Then the matrix element equals 0 since H prime does not change L. Or L prime. It doesn't change it. So that state doesn't change. So when it slides through, boom, it's orthogonal. And so it goes to 0. All right. So we see then that helps, because that means that all of the states are not connected to each other in the degenerate subspace. For example, are these states connected to each other? Yes or no? By H prime. That's right, they're not connected by H prime. And these guys similarly are not connected. And when I say not connected, I just mean that the matrix element connecting them is 0. Not connected by H prime. But what about inside? What about states inside the L manifold? And by that I just mean all the states that have the same L. Are they connected? So now I'm talking about these states, like this guy. Are these states connected? Are these guys connected? Question mark. So let's look at this thing, and so I'm just gonna take the only part that matters of the matrix element, and so let's consider this part of the matrix element. It's this part, L, M sub L, S, M sub S, and this is Lx, Sx plus Ly, Sy, acting on L, M sub L, prime, and S, M sub S prime. And notice how I'm keeping the L's the same, because these are the only states I have to worry about. So you see, I've just taken out this one part, because this part might not be 0, and this part is 0, so I can just remove it. So the only part I have to worry about is that circled part, and that circled part only matters. The problem is when L is the same. When these are the same, then does this thing equal 0? Question mark. And so let me consider a situation. Suppose, first I'll say L equals L prime, as I've shown up there. Suppose this happens. L equals L prime, and M sub L prime is equal to ML plus 1 or ML minus 1. And suppose this also happens, which is that M sub S prime is equal to M sub S plus 1 or M sub S minus 1. Suppose I have this situation, then what happens? And when I say what happens, I'm asking you then, what does the matrix element equal? And so take a look. And so suppose this is the situation, and then I have this matrix element, this thing is hitting this guy's, then does it equal 0, yes or no?
No.
That's right. It doesn't equal 0, because what can happen is then you can construct a situation such that the matrix element then is equal to some constant times L M sub L S M sub S S M sub S L M sub L. You can construct it so that these quantum numbers are all the same, in which case this thing does not go to 0. They are not orthogonal. So that was a pretty long-winded, you can see that that's why I call it brute force. That was like a lot of work. But I just want you to understand that so in the degenerate subspace, then the problem occurs in the L manifold. Problem occurs in the L manifold. And the problem, of course, is that the H prime connects some states. And when I say the word connect, I just want to emphasize when I use that word, what I mean is connect just simply means that the off-diagonal matrix element between those two states does not equal 0. So when the off-diagonal matrix element of H prime does not equal 0, then in my language, I'm saying those two states, in this case, M and N, are connected. All right, that's sort of the language that people often use. Okay. So then,
Professor,
basically, yeah.
isn't the problem also occurring in the S manifold?
Yeah, it is in the S manifold. But the reason why I just sort of am sloppy about S is because, we always have S equals 1/2. It's always the same. That manifold is always there. But the L's can change. Like the electron can have many different values of orbital angular momentum. But yes, you're right. Problem occurs in L manifold and S manifold. You are right. I'll write it there to be complete. Okay, so basically we're screwed, because that means that we cannot use the formula. Well, basically it means that we have a bad basis. And a bad basis means that we can't use our formula. Can't use our beautiful little formula, delta E sub n is equal to psi n H prime psi n. Because this doesn't work, because then all the higher order corrections are infinity. So we can't use our beautiful little formula. So that means we need to find a good basis. Must find good basis. Okay, so how do we find a good basis? We have to find a good basis. We have to find a basis such that H prime is diagonalized in the degenerate subspace, which is the same as saying that the off-diagonal matrix elements of H prime equal 0. So we have to find a new basis in the degenerate subspace for the degenerate subspace. Okay, so the brute force thing, so now we have two choices. Now we have two choices. Before we only had one choice. Now we have two. The first choice is the old choice, which is simply to diagonalize H prime in the degenerate subspace. Just diagonalize it. Construct the matrix. I think in your book he calls it the W matrix. I don't know why he does that. It's so annoying. He should just call it the H prime matrix. Construct the H prime matrix where you take all the degenerate states, the dimensionality of the degenerate subspace, and you just, if there's 4 degenerate states, then you're going to have a 4x4 matrix. And you'll just, you know, construct that matrix and then diagonalize it by brute force, like in linear algebra. But that's painful. We don't like doing that. Diagonalizing matrices is always painful. Painful. Diagonalizing matrices is always a painful process for physicists. We always try to avoid it if we can. So the second process, we have a second choice. Now, the second choice is to sort of hunt around and look for another basis. Just hunt around, sort of like, you know, you're searching for something. Just hunt around and try to find another basis, because it turns out there's always other bases. There's always other ways that you can rearrange your quantum numbers in funny ways, and there's other bases that exist. And you might find one, and it might be good, and then you'll be happy, and not only happy, you'll be lucky. So I'll call this the get lucky technique, which means stumble upon a good basis. This is called the get lucky technique. And I'll ask you a question: which is better, to be smart or to be lucky? What's the answer? It's a trick question. You could say both. You should be both. Because it's funny. I mean, like, I always think it's better to be lucky. I mean, because, you know, luck comes like out of the blue. So I think it's better to be lucky than to be smart, really. But one of the things you'll notice in life as you get older and older, you'll notice that certain people keep getting lucky over and over and over. And then you think, are they really lucky? No, they must be smart. So the two things are kind of combined. But for most of us, I think it's good. It's good to get lucky. Okay, so get lucky. Okay, so let's talk about this second technique. We've already talked about the first technique, which is the painful diagonalization. Let's talk about the second technique, which is the get lucky technique. Okay, so what does it mean to get lucky? So we want to just sort of look around, whatever the hell that means, and find a good basis. Okay, so how do we do that? That's kind of a weird thing to even say, but let's ask ourselves how we might do that. And so before getting into this discussion, first, let's just think about something. The question is, let's do something first. First, let's discuss how we index states. Now, when we have a bunch of states, you know, and like I always talk about states like this, you know, L, M sub L, you know, S, M sub S, psi N, L, M sub L, psi N, L, M sub L, M sub S. You know, there's all these different ways to index our states. We're indexing the states, and we index the states with the quantum numbers. The quantum numbers. well, what the hell is a quantum number? The quantum numbers come from, can you say it? Like, what is a quantum number? We often say quantum numbers, but what do we mean when we say quantum numbers?
It's associated with eigenvalues.
Exactly. The quantum numbers just tell us what they're just shorthand for the eigenvalues. Really, we should be indexing the states with the eigenvalues, but that's too tedious and hard. And so we just do a shorthand. So, the quantum numbers are just a shorthand way of writing the eigenvalues. So really, the states are indexed by their various eigenvalues, and there are multiple eigenvalues, right? You know, there are multiple ones, and those ones are eigenvalues, and what we often can have multiple eigenvalues. And if we, for example, if we want to have an eigenvalue of, say, L squared and LZ, which is, you know, L and M sub L, for these to be good quantum numbers, that means that these two operators do what?
Commute.
Exactly. They got to commute, because if I have a state that's indexed by multiple quantum numbers, then implicit is the understanding that those operators commute with each other. And you guys all knew this, but I'm just reminding you, because these ideas are going to are very important for what comes next. And so that means that if I have a bunch of states, I can always, so if I have a basis, then I can always list my basis. You know, I can have like basis state 1, basis state 2, basis state 3, blah, 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 blah. I'll call these my unperturbed states, you know, up to some M value. And really my index is it's really my eigenvalue, otherwise called quantum number. Okay, so that's how we index the states. So this concept of indexing the states becomes important for finding a good basis. So that was just sort of like some preliminary stuff. So now let's talk about the get lucky technique. So here's the basis of the get lucky technique. It's based upon a theorem. And this is just a linear algebra theorem. So here's the theorem. This is the get lucky technique is based on this theorem. And so the theorem is as follows. Let me just rearrange my little nest. So the theorem is, okay, the theorem is this. And this is just a straight math theorem. So I'll just write it down. It's really easy to prove. It's super easy to prove. And we will prove it shortly. Here's the theorem. Suppose I have one state, psi A naught, and another state, psi B naught, and they are degenerate. Suppose they are degenerate states of some unperturbed Hamiltonian H naught. Okay, so these then would be, and these are meant to be like, suppose these are some basis state that you've chosen. You said, oh, you've chosen some basis states, and you have these degenerate states. And of course, the idea is that you want to do perturbation theory on them, but you want to know if they're a good basis. Now, you could do the brute force thing we just did, which was so tedious, but here's a trick. So suppose we have these two degenerate states of some unperturbed Hamiltonian, but here's the thing. If they are also non-degenerate eigenstates of some other Hermitian operator of another Hermitian operator T and T commutes with H prime, then psi A naught H prime psi B naught equals 0. In other words, psi A naught and psi B naught are a good basis, at least between each other. They're not connected. And you could generalize this to the case where there's many states. Then I'll just say can generalize. You could imagine how you could easily use in some induction proof to generalize this to many states. Can generalize to many states. I should say to.
Also assuming that T and H not commute implicitly.
Yeah, we are. Yes. And so let's just talk about some implicit assumptions. Some implicit assumptions in this are first, definitely T and H naught commute. Now that is built into the theorem already, and can someone tell me why? So it's like, thank you for bringing that up, but I do want to just say that has to be the case, and that's implicit in how I set it up. Why? Somebody answer that question.
Because the psi A and psi B are eigenstates of H naught and T, so therefore, if they're simultaneous eigenstates, then the T and H naught commute.
Exactly, because that's exactly right. You cannot be simultaneous eigenstates of two operators unless those operators commute. Okay, so that's sort of implicit. That's good, but it's good just to sort of bring it out in the open, you know, and mention it. Also, another implicit assumption too is that what does it mean for psi A and psi B? Psi A and psi B are degenerate in H naught, but they are non-degenerate in T. What does that mean? So let's see what that means. What it means is, it means this: T acting on psi A naught is equal to some constant, I'll call it T sub A, the eigenvalue, times psi A naught, where that's just some constant, right? And similarly, T acting on psi B naught is equal to T sub B, psi B naught. And because that's another constant. And so here's the question I will ask you: can TA equal TB?
No.
Exactly. It cannot, because they're non-degenerate. So what non-degenerate means is that TA does not equal TB. So in other words, they have, psi A naught and psi B naught have different quantum numbers. They have different quantum numbers in T. In other words, if I label, and that's why I was mentioning that labeling business at the beginning, if I label state psi naught, psi A naught, and psi B naught, if I label them using the quantum numbers of T, the labels will be different. They will be different, okay? They have different quantum numbers, or I could say different labels different indices. In other words, different labels. Okay, I'm emphasizing this because I have always found this a little bit confusing myself, and so I'm trying to make it as clear as possible. Okay, so now that's it. So then we have found a good. So this is now a criteria. So this is a new criteria for finding a good basis. Because if you can find a good basis, if you can find a basis that satisfies this theorem, then it's a good basis, and you don't have to do all that tedious Bra-Ket algebra that I was doing a few minutes ago. You're just done. You're like, yeah, that's good. I'm done. That's a good basis. So this is a new way to find a good basis, and we will use it in a moment. Okay, so, but before we use it, let's prove it. Because it's so important, let's prove it. And the proof is like totally easy. I love this proof. It's just so damn simple. So let's assume that I have my t and my h prime, and we'll start by just saying, okay, suppose they're 0. So what that means then is that I can just do, I can do the same thing to both sides. Let's do this. Let's do this. Let's left multiply by psi a naught, and then let's right multiply by psi b naught, both sides of the equation. Okay, if I do the same thing to both sides of the equation, then it's okay. And since the right-hand side is 0, that's still 0. So what that means then is that I can have this psi a naught hitting this commutator t h prime psi b naught is 0, because when I do the thing on the right-hand side, it's 0. Okay, so let's just expand that. And so that means that this thing is going to be psi a naught hitting, I have now t h prime minus h prime t psi b naught. And so now I see that for this guy, I can have this t hitting that, but for this guy, I can, because it's a Hermitian operator, I can go to the left. Remember that trick from last semester or whenever you learned it? I can go to the left. And so what does this guy equal? If I go on to the right, what does he equal? Tell me.
T sub b times psi b 0.
Exactly, and because I'm going up here because of these guys. That's exactly right. That's a bad thing about this Zoom thing, is that you guys can't see, like in a classroom, you'd see the whole board. You could look back at all the other stuff, but now you can only see what's in this little tiny frame, which really sucks. So this guy is going to be TB. And what is this guy going to turn into? This guy, what's he going to be?
TA.
Oh, that's exactly right. He's going to turn into T sub A. And so this thing is going to then equal, so then what I can do is, so then I can write this as psi A naught TA H prime minus H prime TB, where those are just constants, psi B naught. Now, of course, then I can pull these out using just simple algebra, and that gives me then TA minus TB times psi A naught H prime psi B naught. Okay, so you see that. But this has to equal 0. Now, look at this. So let me ask you, does TA minus TB equal 0? Yes or no?
No.
That's right, because they're not degenerate. They're non-degenerate, and the definition of non-degenerate is that they don't equal zero. And so this does not equal zero. But if the product of this and this equals zero, then what does this have to equal?
0.
Tell me. Yeah. Therefore, psi A naught H prime psi B naught equals 0. Yay! Get a little 2 stars. Okay, so we proved the theorem. Isn't that cute? It's such a simple little proof. I really like that. Okay, so now let's use this trick. Now we will use the theorem to solve the problem of spin orbit coupling. So first, let's go back to our basis, our bad basis. And using this new insight, we can see why it's bad. So let's analyze why that was a bad basis. Let's do it now a different way. Let's look at it like this. It's a bad basis because we used this basis, psi n, L, M sub L, M sub S. That was the basis that we used. Now, n is fixed because it's a degenerate subspace, but L is a quantum number of what operator? Somebody tell me.
L squared.
That's right. And M sub L is a quantum number of what operator?
LZ.
And M sub S is a quantum number of what operator?
SC.
Yes. Okay, now this quantum number L squared is also fixed. So in the degenerate subspace that we care about, so in the degenerate subspace, the part that we cared about, the problem was occurring in the M sub L, M sub S states. Okay, so that was where our problem was, because those are the states that were connected. If we have N the same and L the same. And so these states, the problem states, the problematical states are indexed by M sub L and M sub S. So that the problem states are the ones that are indexed, labeled by those quantum numbers, and these then are the eigenvalues. M sub L is the eigenvalue of LZ, and M sub S is the eigenvalue of SZ. Now, what we can do is we can just use our theorem now. So let's just take a quick look at our theorem, because our theorem says that from our theorem, we see that the most important thing is this. Does T commute with H prime? That's the most important thing. So let's set that up. So in this case, for this problem, L dot S coupling, maybe I shouldn't say L dot S coupling, but I'll say for this basis, the one we're talking about, our familiar basis, then T is what? What is T? What is T? For this problem, for this basis, the one that we're thinking about. Our old print, this is our basis, psi n, l, m sub l, m sub s. So, you know, these are the labels. And I'm asking you, what is T? I want to apply the theorem to this situation. I'm asking you, what is T?
It's T, LZ, and LS, or LZ and SC.
That's right. And you might be freaked out because there's two, but don't be freaked out. This is just a trivial generalization of the theorem, right? Because, you know, I could sort of have T be sort of multiple operators. Well, if that's not obvious to you, think about it. You know, and if you still have trouble swallowing that, then you can talk to me or you can talk to the TAs. I think Newton would love to talk to you about that. Okay, so this is the T, these operators. And what is H prime?
L dot S.
That's right. In reality, there's also this F of R part, but we can just ignore that because these operators don't act on the radial component. So we'll just ignore it for now, and we'll just worry. It's really the L dot S that's messing us up. So if H prime is L dot S and T is LZSZ, then the most important thing from the theorem is to look at these commutators. The commutator of LZ and L dot S, and the commutator of SZ and L dot S. And for this to be a good basis, those commutators have to be what?
0.
Right, they both have to be 0, or else it's not a good basis. If even one of them is not 0, it's a bad basis. So they both got to be 0. But then this is a homework problem. So this is one of those problems where I want you to grind it out using, you know, homework. You know, so this is a homework problem. And if I've screwed up and did not assign it as a homework problem, then go home and do it as a homework problem, and just prove to yourself. I want you to prove to yourself, because this is really the only way that you'll learn this, is if you do a little bit of this work. You got to prove to yourself that this does not equal 0, and this does not equal 0. And you can kind of see it without even, you know, immediately you can just kind of see it, because it's like LZ, and then L dot S is going to have LX, SX, you know, plus LY, SY, plus LZ, SZ. And you can kind of see that if I do the commutator, you can kind of see, you know already that like LZ and LX don't commute. And you can, you know, LZ and LY don't commute. So you can already kind of see that it's probably not going to commute, but I want you to really grind through all the details and make sure. Because sometimes things do commute that you wouldn't expect when you actually add everything up, you know, sometimes you get cancellation. But I just want you to, you know, I want that to be plausible. So this does not equal 0, this commutator. Okay, and so this is what, so then that tells us immediately that we have a bad basis. And so you can see that this is a much more elegant way of treating these kinds of problems, because now we didn't have to go through all that stupid, you know, broad cut stuff and say, you know, if L equals L prime and M sub L prime equals M sub L plus 1 or M sub L minus 1 and M sub S prime equals M sub, you know, all that stuff we did, you know, all that tedious stuff. We don't have to do that. We can just look at the commutators and boom, we can just know right away, this is a bad basis. Okay, but now the trick then is to find what then is a good basis, okay? So, okay, so we used it to find the bad basis, but really what we want is the good basis. So how can we use this to find a good basis? Okay, so now we're going to do so now comes the get lucky part. Because what we're going to do is we're just going to hunt around like little sniffing mammals that we are, and we're going to sniff around, to see if we can find a good basis. Hopefully we'll get lucky and find one, like finding a nice mushroom under a rock. Okay, and so that's what we'll do. So we sniff around and we're looking for a new basis. And so let's think about it for a moment, because what we did, let's take a look at our bad basis. Again, the bad basis was the eigenstates of these operators. It was L squared and LZ and S sub Z. You know, and I'll just remind you, it was this basis, psi n, L, M sub L, M sub S. That's the bad basis. Bad, oh so bad. Okay, so now let's hunt around and let's see if we can find a good basis. But what does it mean to find a basis? What does it mean to find a basis? We basically, what is a basis? A basis is equal to the set of eigenstates of some operators, right? And so we chose the eigenstates of these three operators because those are the ones that we're familiar with. Those are the ones we learned about last semester. But now we want to find a new basis. So what we need to find is a good basis. We need to hunt around and look for the eigenstates of a different set of operators. And now first, first I will say that we're inside of the subspace. We're inside of the subspace of L. Well, first I just want to say that if I look at, well, the good basis is going to be a basis that commutes with H prime, right? So basically we got to find T such that T and H prime commute. So let's take a look. So we already know that where H prime, of course, is L dot S. So let's start hunting around. So now comes the hunting part, hunt. So let's consider L squared. Does L squared commute with H prime? Does it? Can someone tell me the answer? This is a homework problem. Does it commute? Yes or no? Yeah, it does. It does commute. And so that, and if that's not obvious to you, that's a homework problem. So think about it. And if you look at it closely, you can kind of see why it commutes right off the bat, because I have L squared and L dot S is going to be LX, SX, LY, SY, LZ, SZ. And you can kind of see how L squared commutes with LX. It does. You guys remember that from last semester. And SX, of course, it commutes with S because L and S act on different spaces. So they commute. And L squared commutes with LY and L squared commutes with LZ. So you can kind of see immediately that it commutes. So that commutes. So this is good. So so the quantum number L is okay. That is an okay quantum number. It's a good one. We like him. All right. So let's consider another one. Let's consider, now if we considered LZ and SZ already, and we saw that they are bad. Okay, they didn't commute. Okay, so we can't do those guys. So let's consider, so we have to, so now this is the hunting part. What's another operator that we can consider? This is sort of the get lucky part, the hunting part, because there's like an infinite, there's all kinds of operators, but which is the right operator? Now it's time to get lucky. Okay, guys.
I have a guess. Could we add LZ plus SZ?
Why, yes, we can. Very clever, very good, very lucky. Let's consider LZ plus SZ. What do we call that? It has a name. What do we call it?
JZ.
That's right. Like Jay-Z, who's that? Is that the guy with the tennis shoes? I forget. Okay. Okay. And so, but that Jay-Z is what? So what's another word for Jay-Z?
Total Z angular momentum.
Exactly. Total Z angular momentum. Okay, so if you're talking about Jz, the Z component of the total angular momentum, then we should probably also consider what?
J squared.
Exactly. Let's consider J squared. But before we do J squared, let's kind of remind ourselves let's just define J. J is equal to the total angular momentum. And J is equal to L plus S. So J is a pretty complicated beast, because, L and S are like 3 component vectors and they don't even commute internally. It's kind of complicated. But we can make it sort of simple because what we can do is we can then consider J squared. So J squared then becomes L squared plus S squared plus 2L dot S. And the reason I can just do the 2 is because L and S commute, right? L and S commute. So S dot L. So then S dot L is equal to L dot S. Okay, so that's J squared. And we've talked about total angular momentum already. And so if I define J squared in this way, then what is the commutator between J squared and JZ?
Zero.
Right, because that's always the case for any angular momentum. The angular momentum squared commutes with all the individual components. Even though the individual components don't commute with each other, J squared commutes with them. So you guys know that. Great. So that means I'm considering 2 new operators, JZ and J squared. So let's consider J squared and JZ. So now to see so basically I want to know, the question we want to ask is, are the eigenstates of J squared and JZ a good basis? Now, the hard way to answer this question is to actually take the eigenstates and calculate the off-diagonal matrix elements and show that they're 0 or not. That's the old brute force way, but we don't want to do that. That's tedious. And so what are we going to do? Well, actually, before we do the simple thing, let's consider the hard part. The hard thing is, let's consider the eigenstates. Like, what is an eigenstate? The eigenstates, let's just write out what those eigenstates are. The eigenstates of J squared and JZ, they are just angular momentum eigenstates, J, MJ, right? Because I know that J squared acting on J, MJ is equal to H bar squared J times J plus 1, J, MJ, and I know that JZ acting on J, MJ is just equal to H bar MJ, J, MJ. And so those are the eigenstates of J squared and JZ. But what are these eigenstates, J and Mj? How do I construct them? Well, we did this before. Remember when we added up spin like S1 and S2? It's the same. The rules for adding angular momentum are always the same. Basically, it's a change of basis. So we're going from, basically, we're going from J, we're building J out of the product basis. Product basis. So basically what we got to do is we got to take all the product states, the ones we know about, and those ones are L, M sub L, L, M sub L, and S, M sub S. Those are the product states, and we got to sum over them. And so we're going to sum over all the M sub L and M sub S. Notice I'm not summing over L. L is fixed, and S is fixed. So I'm defining this, so I'm fixing L, but I'm summing over all the product states, and now I have a coefficient, and the coefficient will be this. It's the L, S, how do I, what's the best way to write it? L, S, J, ML, MS, MJ, and I'm summing over ML and MS in a special sum such that ML plus MS equals what?
MJ.
Yes. So that is the eigenstate. That is the new basis we're talking about. Where C, this coefficient is called the, if you remember it's called, those are the Clebsch-Gordon coefficients. And so, but as you can see, calculating all the off-diagonal matrix elements of these new states is very tedious. Nobody wants to do that. So to see, so the question is this a good basis? We're not going to calculate the off-diagonal matrix elements because that's so tedious, but instead we're going to do the very trivial thing. We're going to take this, we're going to take the operators that index them, which in the one case is J squared, and in the other case is JZ. And what are we going to do? To see if this is a good basis, what are we going to do?
Take the commutator of them with H prime.
Exactly. We got to see, we're going to do this. We're going to do our little, our little theorem, which is, and this is the theorem. TH prime equals 0. We're going to check that. And so in this case, we have T is 2 operators, so we're going to have J squared, and H prime is L dot S. And the other one is JZ L dot S. And we got to calculate these commutators. Now, calculating them, I think in one case it's easy, in the other case it's a little bit harder. Just a little bit of work, but this is homework. So I'm not going to do it now. So these are homework problems. And if I forgot to assign these as homework problems, then go make them homework problems. Go home and do them. But after you do them, can you guess what the answers are going to be? Someone tell me.
0.
That's right. And so, and it's not too hard to figure that out. So therefore, this is telling us that the eigenstates of JZ, so now that tells us that the eigenstates of L squared, J squared, and JZ form a good basis. And I do want to keep reminding you what was the bad basis. The bad basis were the eigenstates of L squared, LZ, and SZ. That was the bad basis. And so basically what we find is if we're going to do a change of basis, we're going to go from psi n L m sub L m sub S, and we're going to go to a new basis, psi what? And this is all happening in the degenerate subspace. So what is my new basis? Someone tell me. What's the first? I'll give you a hint. Notice I have 1, 2, 3, 4 quantum numbers. So again, I'm going to have 1, 2, 3. I'm going to have 4. What's the first one?
N.
Yes, it has to be because it's a degenerate subspace. What's the next one?
L.
Exactly, because that's still good. What's the next one?
J.
Yes. What's the next one?
JZ. Or MJ. M sub J.
Perfect. Which corresponds to JZ. That's right. And so this one, and so just to remind you guys, this corresponds to L squared, this corresponds to LZ, and this corresponds to SZ, where now this corresponds to L squared again. Stupid thing. Sorry, I'm having problems with this stupid thing. And this is J squared, and this one corresponds to JZ. Good. So I just want you to see that. That's the change in basis. Okay. So now what we're going to do is so the thing is that then this is our good basis, and so the perturbation. So the way to think about it is that when H prime is equal to L dot S, then the idea is that nature chooses this basis, because that's the basis that doesn't diverge the perturbation expansion, because it does not cause the perturbation expansion to diverge. It doesn't give us infinite energies and weird stuff. And so nature chooses it. Nature says, that's what I want. If you turn on that H prime, then nature says, these are my eigenstates. So nature says, those are my eigenstates. And so, so then if nature chooses those eigenstates and it's a good basis, then finding the change in energy is easy, because now we can just plug in to our simple formula. Now we'll just plug into the simple formula, N, L, J, M sub J, H prime, psi N, L, J, M sub J. You see, because now I have the new basis. And so when I have the new basis, it's really easy to, it's really simple to calculate to do the perturbation theory. So now we can do, so now the formula works in the new basis. The formula works, the perturbation expansion formula, the formula works. Yay, it works. And so now we can calculate the change in energy due to the spin orbit coupling. It's very simple, because we can just do this, or it's relatively simple, delta En. So now let's just do it. So now let's calculate it. So I'm going to write this in this, I'm going to write it like this. Where is it? I'm going to write it like this. It's quite straightforward. So what we can do, well, first I'm going to do a trick. Let's do, well, let's see, let's do the trick. Let's do the spin orbit trick. This is a big trick, spin orbit trick. And I will say this trick will be on the test, okay? I always put this on the test. This is such a cute trick. Every physicist loves this trick. Here's the trick. If J is equal to L plus S, then J squared is equal to L squared plus S squared plus 2 L dot S, just squaring it. But if that's the case, then L dot S is equal to 1/2 J squared minus L squared minus S squared. Oh, such a sneaky, sneaky little thing. But it really helps a lot, because now when I calculate the energy, then this is how I do it. I can say this is my eigenstate, R n sub L. But now I have J m sub J, right? Because that's my, okay, so this is my state. And now my H prime is going to be F of R times L dot S, but now L dot S, I'll use this guy, 1/2 J squared minus L squared minus S squared, acting on R N L J M J. And this is really beautiful, because now look, what happens when J squared hits this guy? He slides right through the radial part and he hits this guy. And what is J squared equal to? Someone tell me.
H bar squared J times J plus 1.
Exactly. And what does L squared equal when he hits this guy? Now, that's not completely obvious by looking at it, but let's go back. Let's go back and look at the structure of the eigenstates. Notice that this is my JMJ state. Notice that he is an eigenstate. See, he's this guy. He is an eigenstate of L squared. See, he's composed of eigenstates of L squared. He's also composed of eigenstates of S squared. What I'm trying to say is that this JMJ state is also an eigenstate of L squared and S squared. And the eigenvalue of L squared is going to be H bar squared L times L plus 1. And the eigenvalue of S squared is going to be H bar squared S times S plus 1. Do you see that? And so now when I go here and I hit L squared onto that state, what does it equal? Somebody tell me, and then we'll be done. Almost. We'll just do S squared too. What does L squared equal when it hits this state?
H bar squared times L plus 1.
Yes. And what does S squared equal when he hits that state? H bar squared times S plus 1. And so then, this is the last thing I'll write, is that I have RNL, F of R, RNL. So I still have to do this. I still have to calculate that. But now this other part, which used to be so hard, is going to be equal simply to 1/2 times H bar squared J times J plus 1 minus H bar squared L times L plus 1 minus H bar squared S times S plus 1. Okay, folks, that's where I'll stop. Sorry for going a couple minutes over, but I just wanted to get that final formula. And you can see it's much simpler than previous formulas. So we'll discuss this further next time. Okay, bye-bye.
Thanks, Professor.
Okay, bye-bye.